In this lecture, we're going to discuss sampling distributions and the central limit theorem. We will focus on sampling distributions for random variables that have an underlying distribution that is normal. Let's look at the agenda. Here is the agenda. We will discuss sampling and statistics. We will then define the central limit theorem and discuss its consequences. Finally, we will discuss different sampling distributions for different statistics when the underlying distribution of the data is normal. There is always uncertainty in any sample collected. This means that any summary measure created based on the sample will vary from sample to sample. Let's talk about parameters in statistics. For the frequentist approach, a parameter is a constant. It is almost always denoted by a lowercase Greek letter. Normally, we don't know the parameter values, so we need to estimate them. We usually do this by collecting data and calculating statistics. A statistic is a summary measure whose value is determined from sample data. Since we don't know the value of the statistic ahead of time, we will consider a random variable with a probability distribution. We denote these with the capital letter. Now let's talk about the central limit theorem. From here on out, I'll refer to that as the CLT. When the underlying distribution of the population is normal with known variance, we can assume that the distribution of the sample mean is also normal. Also, if the sample size is large and the parameters of the distribution are known, the distribution of the sample mean is approximately normal as well. Let's look at some simulations with a skewed distribution. We will use the gamma distribution with parameters alpha equal to 1 and beta equal to 1. We will create simulations of size 1000 sample means with sample sizes of n equal to 5, n equal to 10, n equal to 30, and n equal to 70. Let's see what happens to the shapes of these distributions. Here are the plots. You can see that as the sample size gets larger, the shape of the distribution becomes more bell-shaped. Now let's officially define the CLT. Let x sub I be a random sample from a distribution with known parameter values. If n is large enough, then both the sample mean and the sample totals can be approximated by a normal distribution as seen on the slide. So the question now becomes, how large does n need to be? It is difficult to say. It depends on the shape of the underlying distribution. If it is somewhat symmetric, then the approximation will be good even for small n. For the most skewed distributions, a sample size of 30 or larger will work. Now we can use the CLT to get the limiting distribution of the sample mean. As n approaches infinity, the distribution of the z statistic given in the slide approaches the standard normal distribution. What if we know that the underlying distribution of the data is actually normal? If the underlying distribution is normal and the parameter values are known, the sample mean comes from a normal distribution with mean mu and variance sigma square over n. A similar relationship holds for the totals. Let's look at another simulation. This time we will simulate from a normal distribution with mean 5 and variance 4. You can see from this that regardless of the sample size, we still get a bell-shaped curve as the result. Now let's do an example. Assume that the mean in this case is 28, the standard deviation is 5, and the sample size is 25. We will determine the distribution of the sample mean and then describe the effect on it if we increase the sample size from 25 to 50. Here are the calculations. Let's draw conclusions. The distribution of the sample mean is normal with mean 28 and variance 1. If we increase the sample size to 50, the variance would be cut in half. Now let's move on to the sampling distributions of other statistics. Here we will talk about the sampling distribution of the sample variance when the underlying data comes from a normal distribution. In this situation, the function of the sample variance seen in the slide comes from a chi-square distribution with the degrees of freedom being n-1. Let's talk more about degrees of freedom. We consider degrees of freedom to be pieces of information available in the sample. One starts out with n degrees of freedom in the sample. Each time you use a parameter estimate in the calculation of a statistics, you lose a piece of information. This is why we have n-1 in the denominator of the sample variance calculation. Now assume that we have two samples both from normal distributions, and we would like to compare the variances. As with a single sample variance, we can use a function of the statistic of interest, which in this case is the ratio of the variances, as our summary measure. The measure on the slide comes from an F distribution with the degrees of freedom given on the slide. Now let's assume that we're interested in the distribution of the sample mean and we don't know the variance. If we assume that the underlying distribution of the data is normal with unknown variance, the approximate distribution of the statistic on the slide comes from a t-distribution with n-1 degrees of freedom. This is important again because most of the time we will not know sigma. The t-distribution is very similar to the normal. The main difference is that the t-distribution has fatter tails. The spread of the t-distribution is controlled by the degrees of freedom. The higher the number of degrees of freedom, the closer the t-distribution is to the normal distribution. The t-distribution is also symmetric about the mean. Let's look at an example. Here is an example. We assume that the population variance is unknown, but we do know that the data comes from a normal distribution, so we will use the t-distribution. Here are the calculations. The t-value is 2.25 and the range is plus or minus 1.711. Now let's draw conclusions. Since the t-value falls outside of the range, we can conclude that the claim is false.